In the previous video, we spoke about statistical modeling, and now we'll talk about an alternative approach to modeling, which is known as algorithmic modeling, or even loosely machine learning, right? So let's talk about what that means, right? So let's start with statistical modeling. What did we do there? We made some very simple assumptions, or we came up with very simplified models of the data. So here was one column, or just data which contained only one column, which was blood sugar level, and we came up with this model that this data follows a normal distribution. Or you had two columns and you came up with this model that there's a linear relationship between the two variables under consideration, right? These are very simple models. The advantage of doing that is now you can give some statistical guarantees. This is useful in fields where guarantees matter, right? Which is all sensitive fields like agriculture or healthcare or finance and so on, right? So that's what the approach that you took in statistical modeling. But because you wanted the statistical guarantees, you are limited by the models that you can use. You cannot use a very complex model. So I cannot say that the relationship between my input and output is y is equal to log of e raised to sine of cube of x, right? I can't do that, because the moment I do that, I can't do any statistical analysis on the model. So I was not being able to do that. But it's possible that in many real world cases, the relationship is much more complex than a linear model, right? Or the relationship depends on many factors and you have not considered them. So in such cases, you do an alternative approach, which is to build complex models, and that's where we start going into the domain of machine learning, right? So let's see what I mean by building complex models. So in the previous example, what exactly were you interested in, right? You were interested in knowing that what happens to the blood sugar levels after 30 days. If I can answer this question, I can say whether a drug is effective. I can also know the relationship between the drug and the blood sugar level. And now I don't want to just rely on having this one input, which was the number of days. I know that the blood sugar level will not only depend on the number of days, it could also depend on the age of the person. What is the weight of the person? What is the blood pressure of the person? Height, family history, and other diseases or other medical conditions that that person has. There are a lot of such inputs on which this output could depend. Now what I can say is that I know that there is some relationship between the input and output, right? I don't know what that relationship is. And what I'm interested in doing is coming up with a model for this relationship. And it should be very clear to you and me that in most real world cases, this cannot be like a very simple model like a linear relationship. It cannot be the case that y is equal to m1 x1, where say x1 is the cholesterol level, plus m2 x2, where x2 is the blood sugar level, plus m3 x3, where say x3 is the weight, and so on, right? The actual relationship between the data would be very complex. And what I've done here is my f of x, right, where x is actually now equal to x1, x2, all the way up to all the variables, all the factors that I want to consider. I've chosen it to be a very simple function. This is what I did in the statistical modeling. But now I want to wake up to the reality that in many cases my relations may be very complex, and hence I want more flexibility in this function f that I choose. I don't want myself to be restricted to these very simple functions. So what machine learning does is, it allows you a large family of very complex functions, right? In particular, as you start moving towards deep learning, the functions become even more complex, and now you can model this relationship with very complex functions, right? So that's what you do in machine learning. Yeah. So what is the goal of machine learning? Right? The goal of machine learning would be to estimate this f, this function that I have chosen, using the data that I have and then using optimization techniques. How to do this is a subject of an entire 4 to 5 month course. There are a lot of math involved in that, there's a lot of algorithms involved in that, and how to take the data and come up with these different functions and how to estimate their parameters and so on is a subject in itself, right? I don't want to go into the details, but that's what machine learning does. It allows you to choose very complex relations or complex functions to express the relationship between the variables in your data, and that is what would be the case in many real world applications. And now what you do is, for a new patient, once you have estimated what this function f is, I can just plug in the value of x. That means I can plug in the age, weight, height, blood pressure and all these values, and now just simply compute what the value of y is going to be. So the focus now is on prediction. I am not interested in knowing answers to how much does the blood sugar level depend on the weight, or how much does the blood sugar level depend on the age and so on. I don't care about that. I just care about this, that finally the answer that you give to me should be as close to the true answer. The prediction should be very good. So think about again something like stock price, right? You're trying to predict stock prices, And of course, it's a very, very hard problem. People have not been able to do it, but let's just try to take a shot at it. And now you might have the situation that the stock price depends on various factors. It might depend on the number of seats that the ruling party has in the parliament, or the number of days the US president spent with the Indian prime minister, or the number of amount of foreign investments that are happening in India, and so on. Now, at the end of all of this, you just care about whether the stock is going to go up or not. I don't care about how this is related to the number of days spent by the US president in India, or the number of seats that the ruling party has. I don't care about those explanations. All I care about is this final answer, whether the stock is increasing or not. Now, this is different from the situation that we had in the medical domain, where I care about what the reason is, right? Why is the blood sugar level decreasing? Is it because of the weight of the person, or the height of the person, or what are these underlying relationships in the data? So in applications where that is important, statistic model is at the foreground, and in applications where you don't really care about why certain things are happening, and you only care about the final prediction, and that's where you take this algorithmic approach or the machine learning approach, right? So to give you a quick summary of statistical modeling versus algorithmic modeling, in statistical model you use very simple intuitive model. A line y is equal to mx plus c is very intuitive to understand. I know that m is the slope of the line. If the slope is negative, then the variable one variable decreases as the other variable increases. If the slope is positive, then one variable increases as the other variable increases. It's very easy and intuitive to understand what a linear model is. In algorithmic model, you are not restricting yourselves to simple models. You want the model to be as complex as possible, as long as it captures the real relationship between your input and output variables, or your predictor and response variables, right? So the y is often called the output variable or the response variable, and the x is often called the input variable or the predictor variable, because the output depends on this, right? It is helping you to predict the output. Then the second thing is, this is more suited for low dimensional data, right? Where you have only 4 to 5 fields like cholesterol level, blood sugar level, and so on. That's where you get into statistical modeling. Now, don't get me wrong, a lot of real world applications out there have this small, what you would call as narrow data, right? Where you just have a few columns in your database, and you just want to learn the relations between them. Medical, agriculture, again being examples of where this happens. Hence, statistical modeling is very valued in these fields. Algorithmic modeling is typically used with high dimensional data. So think of images. Image is actually a 300 cross 300 image, or now even 1000 cross 1000 images. Even if you look at a 300 cross 300 image, it actually has 90,000 numbers, right? So this is a very, very high dimensional data. There are 90,000 columns, and each column has some value, and based on that you want to make a certain decision. So that's where you can't really do this very robust statistical analysis, and you'll just use machine learning or algorithmic modeling for that. Here, of course, as I have been repeatedly saying, robust statistical analysis is possible. Here, the models are very complex. They are not amenable to robust statistical analysis. The focus here is on interpretability. I really want to know by how much does my blood sugar level increase or decrease based on some other factor, maybe the cholesterol level, or the number of days the drug is given, or the quantity of drug that was given, and so on. Here my focus is on prediction. I'll just see whether it's increasing or not. I don't care about the relations so much. Throw in all the predictor variables that you have, right? Throw in the cholesterol level, the blood pressure, the age, weight, height, everything, and just tell me finally how much does the blood sugar level increase or decrease, if at all, right? That's what the focus is on. And these are data lean models. You don't require large amounts of data to train these, because they are simple models. I just need to estimate the slope and the intercept, y is equal to mx plus c. So m and c is what I want to estimate, and that's why I need very little amount of data to do that. Whereas these are data hungry models, because you're dealing with large high dimensional data. So you need large amounts of data to learn certain relations between input and output. And this is where you have more of statistics, which is the focus of this course. And this is where you have more of machine learning and deep learning, which we'll do in the subsequent courses, right? So this unified journey, that how does data science relate to statistics, how does it relate to machine learning, how does it relate to deep learning, all that is not very clear in various circles that we talk to, right? And in various courses, this distinction is not made clear between what is statistical modeling, what is machine learning and deep learning. So now it should be clear, right? Where does machine learning and deep learning intersect with the world of data science? When you start learning things from data, when you start coming up with models for data. When you are collecting, storing, processing, describing data, there was no machine learning there, but all of that was useful data science. There's a lot of value in doing all that. A lot of businesses get insights by just doing that. But now once you get into prediction and things like that, that is where you need machine learning, deep learning, and so on. Right? So that's the intersection of these terms with the data science world. And you also now know the position of statistics in the world of data science. Right? Now, if you look at models, typically when you're doing statistical modeling, you'll have simple models like linear regression, logistic regression, linear discriminant analysis. Now, people think that again, statistical model is one class of models and these models are not there in machine learning. But those of you who have some exposure to this field, you would have seen these terms even in machine learning. Indeed, when I'm talking about algorithmic modeling, I'm going to list the same models there. But in addition, I'm going to list many more models like decision trees, k-nearest neighbors, SVMs, naive Bayes, and of course the most popular multi-layered neural networks, which I'll talk about in a minute. But let me just address this commonality between the two, right? So these models are actually simple models. Hence they are very amenable to statistical analysis, robust analysis, whereas as you go towards the lower end of this list, they are not simple models, right? But again, these models also have the form y is equal to f of x. And that was what the crux of machine learning was, to come up with different functions and then estimate these functions using data. How is a subject of a different course, but this is what machine learning does. And even all of these things that you see here, right, all of them are functions. They are just simple functions, hence they have certain properties and are certain useful in certain scenarios. But that does not mean that this is only statistics and this cannot be machine learning. In fact, these models are shared in machine learning also. You could use the same models for prediction also, but you typically do go for much more complex models because you might know that the relationships in your data are much more complex, right? So, and now coming to this part of multi-layered neural networks. So when you have large amounts of high dimensional data and you want to learn very complex relations between your input and output, then you use a specific class of complex machine learning models and algorithms which are collectively referred to as deep learning. And that complex class of models is nothing but multi-layered neural networks, a subject in itself which we'll talk about in deep learning whenever we do that course. And this is collectively known as deep learning, right? So the key thing here is that when your X is high dimensional and when you have lots of X's to train from, that's where deep learning is the most suitable paradigm to use. If you don't have a very high dimensional X, if you don't have a large number of such X's, then you could even do with some of these machine learning models. And if you have a very, very narrow X, right, that means only a few columns in your database, then you just are okay with these statistical models also, right? So that's how this trajectory is. Very simple models, typically with narrow data or low dimensional data and small amounts of data. These models are used with medium high dimensional data and medium sized data, and neural networks really become effective when you have high dimensional data and large amounts of data, right? So that's the main crux of the difference between statistical modeling, machine learning and deep learning. And now what I'll do is I'll give you an example of deep learning and make a case for where it is used in high dimensional data. So here's an example, right? So this is a very popular problem. This is the image of a retina, which is known as the color fundus of the retina. And now based on this, you want to predict whether the patient is suffering from diabetic retinopathy or not, right? So this is a condition which many people suffering from diabetes have, this diabetic retinopathy, and it needs to be detected early so that it can be treated or it can be controlled and so on, right? So now if you want to detect this, then what you're looking at is this image. Now this image is a very high dimensional data. It would be say something like 256 cross 256 or 300 cross 300. That means you're looking at order 900,000 numbers, right? One image has 900,000 numbers. Just understand how big this data is. So if I were to write it down in one stream, this would be very wide data or very high dimensional data as compared to the data that I was dealing with earlier, where I had cholesterol level, sugar level, blood pressure, age, height, weight, and like very small number of columns, right? But now have really large number of columns. This is what is known as high dimensional data. And also fortunately, based on a lot of past patient records and medical records available in the hospitals, if I just combine this data from multiple hospitals, or even if I take data from one very popular hospital right here in Chennai, which is Shankar Nethralaya, they have lots of such data available with them, right? So I have a very broad X or a high dimensional X, and I have lots of such X's. Now this is a classic example where deep learning can really make a difference. I can learn. What am I interested in learning? I am interested in learning how is, let me just see where to write this. Okay, how is the output? The output that I'm interested in is whether this patient has retinopathy or diabetic retinopathy or not. And the input here is this high dimensional image. In particular, this has some 300 cross 300, right? That is what this data looks like. So based on these 90,000 numbers, I want to decide whether this patient has retinopathy or not. So this is really a high dimensional data, and I have lots of such images available through my say contacts in hospitals. Now I want to learn this very complex relationship, right? I can imagine that the relationship between the image and the output would be very complex, because somewhere a few pixels here and there would be collaborating to say whether this has retinopathy or not, and I don't know what these rules are. And that's where I can use deep learning, which gives me a very complex family of functions, not as simple as y is equal to mx plus c, to estimate the relationship between the input and output, right? So that's where it is really useful. And now, talking about why is deep learning so popular today, right? There are three main reasons for that. One is you have large amounts of data available in many scenarios, be it image or speech or language, and typically the relationships between the variables in the data are very complex. They are not very simple. And then you have good software frameworks like PyTorch, TensorFlow, again things that we'll cover in the deep learning course, which allows you to quickly experiment with these models, and you have much better compute, right? So these are very compute intensive models, but all these three conditions have fallen in place, because of which deep learning has become extremely popular and effective today, right? So just to summarize, for modeling data, which is the crux of a data scientist's job, this is the most important piece of the job. You require the following skills. You need to know inferential statistics, for which in turn you need to know probability theory. Then once you get into machine learning and deep learning, you need to know calculus, optimization algorithms, then the ML and DL models. And of course, for all of this to implement an experiment, you need familiarity with various Python packages and frameworks. As I said, I'm going to focus only on Python. There are of course other competing things like MATLAB, R and others, but in this course we are going to focus on Python. So you need to know things like NumPy, SciPy, scikit-learn, TensorFlow, PyTorch, Keras. All of these are things that we'll cover in the courses that we have planned, right? In the current course, the focus would be on the first two bullet points, which is inferential statistics and probability theory, and of course the last point, which is Python. So we'll look at some packages like NumPy, SciPy, and a bit of scikit-learn also in this course, right? So this is the most important part of a data scientist's job. So I'll end this video here, and I'll come back and talk a bit more about why data science is popular today and so on. Thank you.